For those of you that haven't been following my career, actually I used to be focused on Windows. I was in the Windows division until about 3 years ago. Then I moved to Windows Azure, and I've been working there as an architect since I joined. A lot of what I'm going to be talking about today, I'm deeply involved with the architecture of and the future evolution of these areas of the platform. We're going beneath the surface to take a look at how actually Azure works under the hood. I've got this agenda set up for us this afternoon where I'm going to be taking a big step back from the whole system and just looking at the data center architecture, because ultimately the way the platform behaves is directly connected to the underlying physical architecture. And when it comes to the cloud, I like to say the network is the air of the cloud. And so I'll be talking about how we've architected our networks, and that's evolved over time. A lot of that is going to lead into some of the structure of the software that we've developed as well. And that's what I'm going to be talking about as we proceed through this, is not just the physical data center architecture, but then the logical data center architecture, the software that we've built and how it operates the data center. Talk about how we deploy services, VMs, onto that infrastructure, how we update services. So this is how we update platform as a service, cloud applications, how we update the host operating system. And then finally, I'm going to take a deep look at disks, the storage architecture underneath the VMs for both platform as a service VMs as well as the stateless VMs. Now, just so I can get an idea of how familiar people are with Azure, this is, of course, a 400-level class, so I'm assuming that you've used Azure. So how many people have not used Azure? Let's see, raise their hands. Okay. So you all can leave. No, I'm just kidding. I anticipate that there's people here that are just curious about the way Azure works. I will stop, and for the benefit of those that aren't familiar with some of the things that you would be familiar with if you actually had been using the platform, I will spend some time just briefly introducing terms, but this is not a how do you build an Azure application session. This is how does Azure operate, and then, like I said, some tips that I'm going to give you along the way, which the tips are actually, you'll see why they're tips based on the way that the platform behaves for when you do write applications. So let's start with the data center architecture. Like I said, we'll start by talking about where we've got data centers. And this is a little more detailed view than what you saw in the keynote, for example. These are the data centers that we've got. And we've got a principle in Azure that when we have regions, that we've got at least 2 regions in each geopolitical area that are paired together. And each of these regions consists of 1 or more data centers, but what we present to you is the region, not the data center. We hide the data center details behind the scenes. So for example, North Central US there, which is actually in Chicago, there's multiple data centers there, but they appear as the North Central US region. And that is paired with that bubble at the bottom, which is in San Antonio. That's the South Central US region. And by the pairing, what we do is we reserve capacity for failover of our infrastructure services if a data center or the data centers in that region fail. We also automatically replicate asynchronously storage accounts between those 2 regions, blobs and tables, and then queues are going to be coming soon for asynchronous geo-replication between those 2 data centers. So unless you turn that off and you store data in one of those regions, that region fails, we will have your data up to the last 15 or so minutes in the pairwise region. And this is the online regions that we've got. There's 8 of them today. These consist of tens of thousands of servers each. So our total capacity at this point is over multiple hundreds of thousands of servers, and we actually expect probably to double in the next year in terms of capacity. In fact, we're building out many more regions right now. Of course, it takes a while for us to build out new data centers. So anybody that's familiar with infrastructure build out, first you buy the land, you provision the power, you make sure the network cabling, the fibers are all going to the right place, lay the concrete pad, and then only then can you start bringing in servers and bring them online. We've announced these regions, which are either in the process of being built out and close to operational or already in preview operation. For example, you see China. We've got 2 regions in China that are paired together that went online. Well, actually, they're about to go online for public usage imminently. Steve Ballmer just went there a few weeks ago and basically opened them for preview. So they're online and operating at this point, going through final stages of vetting before customer applications that the general public can start to deploy there. You can see we've got Australia as well and Japan that we've announced as well, pairwise regions in both of those. As far as the way that these data centers are built, what we've been showing you, if you've ever seen a data center, Microsoft data center videos, you've seen these containers. And in some cases in the past, you might have heard Azure uses containers, where we just roll in a whole container full of dozens of racks and drop it down and we're ready to go. In Azure, we've figured out that actually that's not cost effective. Actually, the cost of the container itself doesn't merit the agility that you get out of just being able to bring those in. Instead, what we do is we have the hardware partners that we work with, build the racks and ship the racks to us. They're not in containers. We put them in data centers that are enclosed. That video right there is about a 10-minute long video that I encourage you to go watch if you'd like to see the gory details. I've just got some pictures that I pulled from that video just to show you that there's nothing magical here. There's a picture of the racks inside of one of our data centers. That's the way that they all generally look. We also have, well, actually there's one data center that I've come across that I wasn't sure where this was, that looks different than all the others. If you go to windowsazure.com, the first data center you see is this one right here. And I was like, when I saw this pop up, I was like, where is that the curved hall data center, and why would we curve the halls of the data center? So I looked into it, and I arranged for a tour of this data center, and I took a picture while I was there that I think explains it pretty well. And that is this picture right here. And actually, there's a rotating restaurant, too, in this data center, which is kind of nice because you get a view of the surrounding area. But no, we really don't have any curved data centers. That is, I don't know what that is, Photoshop or something. But this is a standard data center. Here's what we've got as far as power redundancy in all of our data centers. We've got 3 levels of power redundancy. APCs that you see there for short blips of power. Behind that, we've got batteries for longer power outages. That's a whole vat of batteries. It's like something out of the Matrix there. We've got bodies in there that are energy is being sucked out of them just in case we need them for the servers. And then we've got generators, too, which are big diesel generators with natural gas that we've got there, enough to power the data centers for several days in case there's actually a grid or a substation power outage problem near the data center. So multiple levels. We've actually also, behind this, have a bunch of squirrels just in case. We've got about 1 billion squirrels. And the reason we get squirrels is because paying for that, they cost essentially peanuts for the squirrels. And we've got about 1 billion, so that's a giga squirrel of backup redundancy that we've got as the 4th level. We also have data center security, very rigid controls. So if you go to visit a Microsoft data center, there's guard posts, there's concrete barriers, there's guards that are actually armed on the way into the data center. When you get in the data center, you go through basically an airlock that weighs you so that you get weighed on the way back out. And if you weigh more on the way out than the way in, you can weigh less on the way out than the way in. There are bathrooms inside the data center. But if you weigh more on the way out than the way in, then something funny is going on, and they'll search you and make sure you're not lifting a disk or something. There's biometrics for access to the server rooms as well. So we take security very seriously. As far as the physical network, which is the core structure of the data center, in fact, the racks are laid out to accommodate the network topology. Our networking design has evolved through 3 generations since the Azure project started back in 2007 or too late 2006. The original network design is one that Azure inherited from Microsoft Global Foundation Services, the group within Microsoft that's responsible for building the data centers and operating them on behalf of the properties in Microsoft. And back in 2007, 2008, the major properties in Microsoft were very internet-focused properties. So traffic comes in from the internet, there's processing, and then the answers go back out to the internet. So they were very optimized for this kind of traffic. Well, what we see, and that's called north-south traffic, what we call it. It's north-south, meaning up and down, into and out of the data center. But what we see when we started developing this platform, Azure, is that we've got compute that talks to compute. as we develop these scale-out applications, we also have compute that talks to storage within the same data center. So heavy amounts of bandwidth usage within the data center or east-west kind of traffic. The network wasn't designed for that, and so we had to accommodate it with changes to the network architecture. Also, the network topology heavily oversubscribed. Even the north-south traffic was heavily oversubscribed, meaning the amount of bandwidth that could be generated from the servers in the data center would overwhelm the switches. And the fact is that that was rarely the case that would happen. But with Windows Azure applications, we needed to bring down that level of oversubscription to get more predictable performance for our customers or applications that are running. So I'm going to give you a quick tour of that network architecture. This is the original one that we inherited. It's called DLA, Direct Link Architecture, Generation 1. And the interesting thing to note here is that there's artifacts of this architecture still in the logical software architecture of Azure, which I'll get to a little bit later. If you look, there's 3 levels of network architecture or networking down to the top of rack router, which is what you see racks across the bottom. There's about 20 racks under each one of these aggregation switches, which have load balancers, hardware load balancers, hanging off them. And the reason that you see LBs on both sides is that everything's redundant in this architecture. There's 2 AG switches, each one with 2 load balancers on them in case one fails. Then there's access routers, 2 of those, and then at the very edge of the data center, there's these massive data center routers that have tens of gigabits that go out to the internet. You can see that the rack architecture underneath these AG switches, there's 20 racks under each one, and then there's 3 units of these 20 racks underneath the access routers. That'll come back and be interesting later. Now you can see that the level of oversubscription as you go up this architecture up to the data center router is 120 to 1. Not only that, so if everybody starts pumping data out to the internet, it's 120 to 1 oversubscribed, but worse, because of this architecture, if you look at a server in that rack over in the far left, that's talking to a server on the rack over on the far right, the traffic has to go all the way up to the data center router and then back down. So even if traffic isn't aimed at the internet, it still has to traverse through the data center router, which causes that oversubscription problem in the case of Azure east-west traffic. And the amount of bandwidth that can be supported across that data center, those data center routers, is about 120 gigabits. 60 gigabits per DCR. So you see that the way more than 120 gigabits of bandwidth if you assume that each server even only has 1 gigabit switch off it. So this architecture was just not able to scale for Azure. This is what we started rolling out and retrofitting our data centers with a couple years ago. It's the Generation 2 network. It's called the Quantum 10 network. The major difference between this network and the previous one is that this one is called a Claus network after this guy named Claus that has a fully bisected network, basically, multiple points between every point on the network and every other point on the network, a flat network design it's also called. And with this, we get rid of the oversubscription at the top of the network. So traffic going east to west in the data center, there's no oversubscription except for at the top of rack routers. Top of rack routers, there's about a 3 to 1 level of oversubscription, which we found, basically that means that you're only going to get congestion when all of the servers, when a third of the servers start pumping full blast out of those switches, which is something that's very rare at the scale of a rack with about 90 servers in it. So this architecture we found scales extremely well for the kind of traffic that we got in Azure. Of course, we could go all the way to the other extreme and not over-provision at all, but that kind of defeats the whole point of the cloud. Because with the cloud, you've got big scale, you can over-provision safely. It's called statistical over-provisioning. What we've done, too, is every data center like this, you've got storage and compute, and we've got a ratio of about 2 to 1, we found, between storage and compute. We call these things the stamps that are under the top of rack routers, blue for the compute, green for the storage. This architecture supports about 30,000 servers. And it supports, if you look at the total bandwidth capacity from east to west, because there's multiple paths from the left side of that architecture to the right, it's about 30 terabits compared to the 120 gigabits we had of the previous architecture. 30 terabits can flow east to west across this architecture. So really scalable design. It's actually a design that we worked on with Microsoft Research. Even this, though, isn't able to scale to the sizes of the data centers that we've got under construction right now in Azure. So this is what we're rolling out right now for our new data centers and starting to retrofit the Quantum 10 data centers with this architecture. It's the Quantum 10 version 2. The difference between this one and the previous one is we added another layer. It's the quantum spine, or the cluster spine there. You see the CS, kind of magenta colored things above the top of rack routers. That increases the level of oversubscription, so it's still 3-to-1 at the Tor, and it's about 4.5-to-1 at the cluster spine. But there's a larger number of servers underneath, so the chances of us getting close to that level of oversubscription is actually even lower than it is at the Tor, because it requires massive amounts of servers to start spewing across the network. In this architecture, this one scales to about 100,000 servers, and so this is the kind of scale that our data centers are growing to at this point. We divide the data center logically, so switching from the physical topology, which you just seen, to the logical topology, we divide the data center into logical groups of servers called clusters. We also call them stamps. The size of a stamp is 20 racks, and 20 racks comes to about 1,000 servers. So each of these clusters is about 1,000 units, 1,000 servers. We also call these hosts or blades or nodes. So there's servers, nodes, hosts, and blades. That's the 4 terms that we use within Azure to refer to what you call a server. This architecture of 1,000 servers in a cluster, if you go back to the DLA architecture here, it corresponds to this right here. What's underneath one of these aggregation switches? 20 racks. So that's what we still treat today as our logical unit of management. The reason that we divide the architecture logically into these units is because one of the principles of cloud design, and this is something that you should be taking to heart when you build your scale-out services, is partition, partition, partition. Partitioning your software helps you tolerate failures better. So by minimizing the blast radius effectively of a failure. If we have a cluster that fails, and back in the DLA architecture it meant both AG switches failed, for example, we'd lose all those 20 racks. We apply that same kind of partitioning to software here, where if we have a software fault for the software that's managing these 1,000 servers, we've only impacted those 1,000 servers, not the entire data center of 100,000 servers. So this minimizes the blast radius of kind of catastrophic faults. And this is a principle that we try to follow everywhere in Azure, is to partition for that kind of availability. Each of these clusters is managed by a software component called the Fabric controller. And that's the team that I'm mostly closely associated with. And Fabric comes from the term, I mean, if you look at the data center diagrams that I've shown here on the previous slide, that is like a fabric right there of networking connecting all these servers together. So we've got the Fabric controller that manages this. I used to work in Windows, and I was closely associated with the kernel team in Windows. My natural affinity then was to come to Azure and work at the core base of the Azure operating system, and that component is the Fabric controller. It has a very similar role to the kernel does on Windows desktop or server. In Windows, the kernel is responsible for first managing the physical hardware, then virtualizing the physical hardware, and then defining what an application is that runs on the system. So what is a process? The Fabric controller does the same things. It manages the physical hardware of the data center. It gives applications a virtual view of that data center hardware, and it also defines what is an application. So its multiple roles or responsibilities are management of the hardware, management of the applications. And it takes 2 types of input. One type of input is at the time we're provisioning the hardware. It's just like when you boot Windows and the kernel goes and reads from the BIOS. Oh, this is what the system has, how much RAM it has, and how many CPUs it's got. The Azure Fabric controller also gets a description of the data center hardware that we feed it. Where are all the blades? Where are the Tors? Where are the switches? So that it can manage those. And then the second input is one that you give the Fabric controller, which is your application, your PaaS application or your IaaS VM descriptions. And then the Fabric controller goes and maps the application onto the virtualized and then ultimately the physical hardware. As far as the way that the fabric controller is architected itself, I get this question. In fact, somebody just asked me a little while ago, what kind of programming language is Azure written in? Azure is a very broad platform, has very thick stacks. So there's higher level services like Windows Azure Active Directory and Service Bus, all the way down to the fabric controller, and then components that run inside of the server next to Hyper-V, the virtualization layer. And you'll see two languages being used throughout Azure, C++ and C for the very low-level components, and then .NET basically used everywhere else. The fabric controller itself is written in C#. And the fabric controller, as far as the way it's divided, for that high availability, there's 5 instances. We dedicate 5 servers of each cluster to the fabric controller. And then the fabric controller acts like one single unit across those 5 instances, presenting one view to the outside world. So there's a primary instance. So one of the servers, fabric controller replicas we call them, is the one that is actually, I'm in charge. When somebody deploys an application, I take it, I decide where it goes, and then I synchronize my decisions with the other replicas. And we make sure that we don't proceed unless we've got a quorum. To have quorum, we need at least 3 instances to agree or to acknowledge, hey, I've got it. I understand what the decision is. By having a quorum of 3 and having 5 instances, we can tolerate multiple failures of servers running the fabric controller and still continue to operate without interruption to application services. We can also, and this is what it's really designed for, we can be upgrading the fabric controller and tolerate a hardware failure at the same time, a server going down. Just like when you update your PaaS applications, you've got this concept called update domains, which are slices through your application. And when you say, go push this update to my app, what the fabric controller does is walk update domain by update domain, applying the new config or code. We apply that same kind of update domain philosophy in the fabric controller. So there's 5 instances here. When we roll out an update to the fabric controller software, it goes to instance 1, then instance 2, then instance 3, then instance 4, each step of the way, making sure that that instance is healthy before we move on to the next one. So if we're in the middle of rolling out an update, we're down to 4 instances because 1 is being updated. We can tolerate another server failure. We're down to 3 instances. We still have quorum. We can still make forward progress without interruption. So it would take multiple hardware failures and a software update to interrupt the fabric controller's operation. Let's take a look at the description that we feed the fabric controller. So how many people in here do data center design or layout or figure out network topologies in your data center? So a few people do. So this will probably be kind of familiar to you. What we do is we've got basically a giant XML file that describes the data center. And we feed this XML file to the fabric controller to tell it what it needs to manage. I'm going to search for a particular cluster. And this is if you take a look at this format for this name, CO2, this is the data center. So data center 2 in Columbia, which is Quincy, Washington. This is where we've got Azure test resources. Stage says this isn't production. This is a stage data center. This is one where we go and deploy bits to do testing with. And then app says this is a cluster or a stamp that is assigned to compute, not storage. And then it's the second one inside of this particular data center. So that's the naming nomenclature. And when the fabric controller starts up, we tell it, hey, you're CO2 app stage 0, or CO2 stage app 02. And we feed it that information about its topology. If we take a look down here, you can see there's VIP ranges that we assign. So this is how it allocates publicly routable IP addresses to VMs running in that, from start IP address to end IP address ranges. And then, but this is really the interesting part here, which is the description of the hardware in that cluster that it's going to manage. So here's the network switch. Here's the address of the network switch. Here's the serial concentrator. So when we need to interact with the BIOS, with the firmware screen, sometimes on these servers, there's a serial concentrator, which gives us a display. It's through a KVM kind of app. that we can do that through. There's 2 power strips, one for each batch of 40 or... Oh, I was supposed to scrub this. Sorry about that. Let me get rid of that. Pretend you didn't see that. And then we've got the list of blades in that data, that particular cluster. And it consists of the blade IP addresses. So they each are on private VLANs that aren't visible to the VMs, that the Fabric controller can talk to those blades when the server software comes up on them, and as well as blade IDs. This is the blade IDs that we use when we're referencing the Fabric controller. That gives them unique identifiers. That's what the Fabric controller, we feed it, and that's how it bootstraps Fabric. Now, speaking of bootstrap, so the Fabric controller, we give it this description of, hey, you're supposed to manage this stuff. How does it get that stuff up and running? How does it get a server ready to accept VMs that customers deploy? What I've got up there on the far right is the Fabric controller replica in one of the instances. On the Fabric controller servers, they've got what is called an image repository. So this is where we store VHDs and other artifacts, like your packages that you upload as part of your applications. We store them in the Fabric controller on those disks on the Fabric controller replicas. We also have on there a Windows deployment service as well as Pixie server. And the Fabric controller, using those PDUs, the power distribution units, can power on a node. The nodes or the blades or servers are programmed to Pixie boot, and they Pixie boot from the Fabric controller's Pixie server. What they Pixie boot is something called the maintenance operating system, or the MOS. Now, what operating system is the maintenance operating system? It's Linux, of course. No, it's not Linux. It's the maintenance operating system. What's the stripped down version of Windows? The one that people use for deployment? Yeah, Windows PE. That's what we boot these servers off of, is Windows PE, Pixie booting off of Windows PE. We call it the maintenance OS because it has some extra junk in there. And what the maintenance OS does at that point is it formats the hard disk and then downloads VHDs for the host operating system. Everything in Azure is boot from VHD. When Windows 7 came out, it introduced boot from VHD in Server 2008 R2. It introduced boot from VHD. This technology was developed inside of Windows Azure. Everything is image-based in Windows Azure, and this was another principle of cloud operation, is image-based management of your system. What image-based management, just like we pass this philosophy on in our PaaS applications, is that you can always start from a known good state if you start with image deployment, rather than, hey, I've got a server and I add some cruft to it, and then I update it, I add some more cruft, I change the config, and at some point you kind of lost track of what that configuration looks like, and holy crap if you lose that server because there's no way to bring it back to where it was. With image-based management, you always can get back to where you were because deploy the new image, apply the config, and you're back in business. And so everything is image-based through VHDs. So the VHD comes down, the server reboots into the VHD, it does a sysprep specialize, just Windows server, just like you do. We don't cut any corners here, we actually do sysprep, and these servers come up sysprepped. Once they come up, they've got a Fabric host agent, or the FC host agent there that you can see, that is programmed to go talk to the Fabric controller. It'll generate a self-signed certificate, talk to the Fabric controller knows that this is the server it is because it trusts the network, the configuration of the network, and at that point it establishes a secure SSL, mutual auth SSL tunnel between the Fabric controller and that host agent that it can start sending commands to. At this point, the server is ready. It is now something that's entered the Fabric controller's inventory of servers to which it can deploy virtual machines. Let's talk about virtual IP addresses now, because when we talk about networking and the Fabric controller managing networks, you saw the virtual IP address range here. What is a virtual IP address, or VIP? A VIP is the publicly routable IPv4 address that you get when you deploy a cloud service or a VM that becomes a cloud service in Windows Azure. It is what you can bring your DNS CNAMEs and map them to, or what you can see from anywhere outside on the internet. There's two ways to communicate between VLANs. One is through the VIPs, because These are publicly routable. Now, if you're talking between VIPs within the data center, you're not going out across over the internet and coming back in. Of course, you're going to be talking through the data center itself. But there's also internal IP addresses called DIPs, or dynamic IP addresses. These DIPs are assigned to the servers, and you saw some DIPs there in that datacenter.xml. They're also assigned to VMs. VMs get their own DIPs. And the DIPs are put on VLANs. Each cloud service is on effectively its own VLAN that's enforced by something called the virtual switch driver that sits inside the server next to the host agent. And that is what enforces these networking boundaries within the data center for applications. So one application can't talk to another one unless they've made an agreement to do so. One of the questions that I often still get is from customers is, I've deployed a cloud service. I know that you gave me an IP address, Azure. Can I trust that that IP address won't suddenly change because I'm setting up ACLs in my internal my CorpNet firewall and routing rules, so I want to make sure that it doesn't change, or I want to know if it can change because that's going to cause everything to break. And the answer is, and this is official, you get that IP address as long as your cloud service has at least one VM deployed in it. And by deployed, I mean it's actually sitting there active. You will retain that IP address. It just won't suddenly switch out from underneath it. Now, the next question I get people ask me is, well, what about dev test? I want to shut everything down and then bring it back. What about then? Today, you will lose the IP address once you shut everything down. And when you spin it back up, you'll get a different IP address. Now, we are working on reserved IP addresses or assignable IP addresses, so that's coming at some point, is you'll be able to say, no, I want this IP address, and even if I don't have any active cloud service, I retain ownership of it, and then I can go assign it to cloud services as I spin them up. So that will be coming, but today, just know as long as you have something deployed, you preserve that IP address. I mentioned load balancers back when I was talking about that original DLA architecture. Some of you might have noticed that when I talked about the Quantum 10 network and the Quantum 10 V2, there were no load balancers in the picture. What happened to the load balancers? Well, they went the way of software-defined networks, which is SDN. It's the hip thing. Companies get sold for $1 billion because they're doing SDN stuff. SDN is the wave of the future when it comes to network control. And Windows Azure was one of the first fabrics, one of the cloud computing platforms that really took advantage of this. And we developed SDN for our load balancers first to get rid of these costly hardware load balancers. Those hardware load balancers, they had several problems. Very expensive devices, very fragile. They don't scale, so you throw enough ACLs at them and routing rules at them, and then they barf. And they're running, a lot of times, not the most reliable software on them. How many people love hardware load balancers? Anybody love hardware load? How many people hate hardware load balancers? Okay, yeah, a lot of people have probably horror stories of hardware load balancers, and we've got plenty of scars in Windows Azure that made us say, all right, time to get rid of hardware load balancers and switch to software load balancers. The benefits are incredible of switching to this software architecture, which I've got shown right here. It's really 3 different components can make up the software load balancer. On the far left, you see the fabric controller itself. What the fabric controller, the part that controls virtual machine deployment, it's called we call that the tenant manager. So the tenant manager is responsible when somebody deploys something. Hey, I'm going to go deploy those VMs. And over there on the far right is the node. And there's the VMs that appear. Now, when those VMs appear, the fabric controller knows what dynamic IP addresses are assigned to those VMs, as well as what virtual IP address or addresses are assigned if they're part of the same cloud service or different ones. It tells the SLB manager or SLB controller about the fact that those VMs are coming into existence by talking to the network manager component, which sits on the fabric controller blades, their servers. What the SLB manager does is talks to the SLB host plugin, which is a little agent that sits on the servers themselves, connected to the VM switch that you see over on the right. This is like the Hyper-V VM switch, except this is the Azure flavor of it, and gets the routing rules for that which it programs into the VM switch, which says incoming traffic aimed at this DIP goes to this particular VM. Then it tells the SLB MUX role, the multiplexer role, about these routes, the public IP address route mapping to the internal IP address route mappings. And there, of course, when you've got multiple VMs behind a load balance set, or they're part of a role with a public input, load balanced input endpoint on them, then what the controller, or the manager, tells the MUX is, here's a public IP address and a port, and I want you to load balance or spray across these dynamic IP addresses behind it. And that's what the MUX's job is when a connection gets established, a TCP connection gets established, or a UDP packet comes in, is to do this hash algorithm, which is a 5-tuple hash, source port, source IP address, network protocol, target IP address, target port, and then figure out which VM is going to get that traffic. And then it forwards the traffic as it comes in from the internet. It also is controlling the actual hardware switches to program these routes so they get routed right down to the correct top of rack router, for example, and then to the right blade. And then the VM switch in the VM routes the traffic to the appropriate VM. Traffic that goes out, and this is done through GRE, packet encapsulation. So the packets that come in have the virtual IP address on them. And what's done is they're wrapped then with the dynamic IP address so that they get to their destination. Then on the way out, we strip off the dynamic IP address and send it back out directly, bypassing the MUX, so it comes out to the internet looking like it came from the virtual IP address. This is the way that the software load balancer works. The cool thing about this is that the software load balancer is written as a Windows Azure application, just like yours, except it's using basically the core infrastructure capabilities, not the higher level services, because it's so deep in the system. But it is a scale-out application. The MUX consists of multiple instances. It's running in VMs. It's actually running in VMs that basically we give the VM the whole blade, the whole server, as you'll see, just because we want to maximize the network bandwidth for these MUX roles. The SLB manager itself is also scaled out for high availability, like the Fabric controller, consists of multiple scaled out instances, so it can tolerate multiple failures during update, just like the Fabric controller. But it's that same basic software architecture principle being applied to the infrastructure itself. Now, as far as the overhead of the software load balancer, let's take a look at how much latency the load balancer adds to traffic. And I've got two VMs up here. They're part of the same cloud service, so they can talk to each other using their dynamic IP addresses or their public IP addresses. And to test the bandwidth, to test the latency between these two VMs sitting in the cloud, I've got a little tool that I wrote called PSPing. Has anybody run PSPing before? It's a sysinternals tool. It's PSPing, so for those, lots of you aren't familiar with it, I wrote it specifically so I could do cool demos like this. It is a tool that measures network latency or network bandwidth. Or it will just do TCP port pings. So if you've ever wanted to say, hey, what's the latency to that, port 80 on that machine? Ping won't do that. Ping does ICMP. PSPing, you can say, what's the latency to IP address port 80? And it'll tell you that. The way I'm going to run it right here is as a latency test between these two VMs. Now, you can see that this is the dynamic IP address. Where did I get that dynamic IP address? This is this machine. If I go to the virtual machines I've got running, looks like the network's actually cooperating with me in this session, which is really nice. So over here, there's the internal IP address. This is the DIP, and this is the VIP. And you can see we call it a VIP right there. So there's two ways to talk to that VM. And I've created a port on that VM so I can talk to it from the internet. I call that endpoint PSPing. It's port 5000 on the public IP, maps to port 5000 on the dynamic IP address. So let's do both tests to see the latency. So first, let's just hit the DIP. And the reason I can hit the DIP is from this other machine. Actually, I've already got this in the history. There it is. Once I press OK, so what this is doing is saying 16K packets, do 10,000 of them, and send them to this IP address and port. And you can see that this side is measuring things at the same time this side is. And you can see here's the average latency of those packets. PSPing, by the way, can do histograms. And it's got some flexible histograms. It'll, by default, dump it into 20 buckets of latency. So you can kind of see the spread. So most of the packets were under a third of a millisecond. But you can see the average here, 0.51, driven up by some of these long tail packets that took a little bit longer to reach their destination. How much overhead do you think going through the software load balancer will have? Anybody want to guess? How many milliseconds will it take for me to do a PSPing through the SLB? How many? I heard something over here. 2 milliseconds. Anybody else? 1 millisecond. Okay, well, let's go see. Anybody for 5 milliseconds? 5? 5 sounds like a good number, doesn't it? Let's see. PSPing, and I'm going to get rid of the dip and put in the VIP. Well, I guess I didn't copy correctly from the portal. Control C and Control paste. Whoop. Port 5000 and 1.1. So you both are right. It's a little over 1. So the amount of overhead that the SLB adds is about half a millisecond on average, which is actually a pretty good low level of overhead. We measured ourselves against the hardware load balancer because we didn't want to put in a software solution that stunk compared to the hardware solution as far as latency. I mean, the hardware load balancer was half a millisecond of latency and the SLB was 5 milliseconds of latency. Well, then we might think twice about going to a software-based approach. But the hardware load balancers we were using before, they added about a half a millisecond of latency as well. So 500 microseconds is actually about what we see a network device add, and that's what the software load balancer is adding. Nevertheless, if you're very latency sensitive, and you can talk between machines through the DIPs instead of the VIPs, and one way to enable that, even across cloud services, is of course with VNet. When you apply a VNet, you can then talk to the DIPs directly using the overlay IP addresses that you're skipping the load balancer. No reason to have the load balancer in the way of your traffic, slowing down potentially bandwidth, slowing down increasing your latency if you don't have to. And so that's a tip right here. And that tip, by the way, so I'm going to have several more of these tips. I wanted to make this kind of interesting under the hood, kind of look at the platform, but also at the same time, hopefully a few nibbles you can take back and that'll be useful to you. Next, let's talk about deploying services. So when you package up an application and deploy it to Azure, you can go through various different means of getting your package to us. One is through the Windows Azure portal. You can go upload your package. Another one is through App Controller, System Center App Controller. Another one is through just talking to RDFE directly. Now, what is RDFE? I'm going to talk about that in a second. But RDFE takes the package, stores it in its own Windows Azure storage account. That is automatically asynchronously geo-replicated. Now that it's in the storage account, it hands the package, the cloud service, to a Fabric controller. The Fabric controller converts it to its own model, stores it in its image repository, which I already talked about, and now the Fabric controller is ready to start deploying that cloud service and the VMs that make it up. So here's a tip, is keep that package small. And in fact, deliver as much as you can out of band. Because if you look at the path that a package will go, here, so you got the core package. If you upload it through the portal, you're basically passing that package through the portal. It doesn't get persisted by the portal, but that's just another delay as it flows through the portal. Then it gets taken to RDFE, the front end, which stores it in its storage account. Then it deploys it to the Fabric controller, which stores it in its image repository. Then it actually sends it to the actual server that those VMs are going to get created on. So you can see there's multiple hops. 2 of them are persistent, RDFE, well, 3. It gets stored on the server's disks, gets stored on the Fabric controller's disk, gets stored in Windows RDFE storage account. So if you're sending a 600 megabytes, which is the largest packet, I think it's a gigabyte and maximum of 600 megabytes per roll, that you're flowing that data through this network and hitting that storage, might as just keep it small. Just send your code and your core config and pull any data from Windows Azure Storage. So auxiliary files that aren't part of your code, you stick in Windows Azure Storage, and then the cool thing about that is that you can pull that in on demand. The code that's sitting on that server, if you don't need those files, then they're left in Windows Azure Storage. You're not paying this price of funneling them through the network and storing them on these disks. But you can pull them in on demand. You can update them very quickly without having to go through the deployment pipeline. So deployment pipeline, keep it to the core code and the configuration of that code. Keep all auxiliary data out of band like this. Now, what is RDFE? I've been referring to this term, RDFE. It stands for Red Dog Front End. Red Dog Front End, by the way, just as a little side trivia note, is Red Dog was the original project name for Windows Azure. Does anybody know how it got the name Red Dog? Okay, nobody knows? All right, so I'll give you a little secret. Don't tell anybody this. But Red Dog was the code name that came up for the project. Dave Cutler was actually the inspiration. Some of you might have heard of Dave Cutler. He was the original architect of VMS, and they were on a tour of San Francisco looking at Microsoft data centers. They passed a place called the Pink Poodle, and Dave said, hey, that's a cool name. Let's call the project Pink Poodle. Of course, he was immediately overruled by everybody with any kind of sense of, that sounds ridiculousness. But what is the Pink Poodle? Let's go do a search for Pink Poodle. Actually, I better not. I'll leave that to you. If you want to do a search for Pink Poodle, best not to do it at work. But that's where it got its name, Red Dog. So they said, let's call it Red Dog. What Red Dog does is manage subscriptions. So when you create a subscription in Azure, RDFE is responsible for it. It does billing, so it emits all billing records to our commerce system. It does authentication to the platform, so it's the service front end, and it also is where deployment happens. It picks which cluster that a package will go to, and it's got several rules. First, you specify which region it can go to, and it's got a choice. Within the region, it'll pick a fabric controller cluster based on the load of that fabric controller cluster. Or if you've specified an affinity group, it automatically goes to the affinity group that is the region that's associated with that affinity group. And let me talk a little bit more about affinity groups. How many people have used affinity groups? So quite a few of you. So where do affinity groups come from? If you look at the original DLA architecture, that's what an affinity group was. Everything under the aggregation switch or the access routers. So there's 3 stamps, 3 clusters, 2 compute and 1 storage. The reason that we exposed that back then was so that your compute and storage would be located, if they were in the same affinity group, underneath the same access router, so that traffic between compute and storage wouldn't have to go all the way to the data center router. It would optimize bandwidth and latency in that DLA architecture. Of course, that's not a reason for them anymore because we've gone for a different architecture. So what affinity groups do today is if you specify the same affinity group for 2 cloud services, they will go to the same fabric controller stamp. And I'll explain why we still have that today. If you specify storage and you put storage in an affinity group, the compute will go to the same data center, same region as the storage the affinity group the storage is in, or vice versa. If you deploy compute and you put in an affinity group and then create a storage account in the same affinity group, they go to the same region, not the same access router like it used to. So why would you put objects in an affinity group? Well, a compute cluster is the scope of a virtual network today. So if you create a VNet, that VNet has to live within a fabric controller stamp. So if you created a VNet and you try to create a cloud service, it will always go to and you put it in the same VNet, it'll go to the same stamp. If you've got an affinity group, you can't put cloud services from different affinity groups in the same VNet because that's a violation. Basically, VNets and affinity groups kind of map one-to-one when it comes to compute. Also, clusters the scope of homogeneous hardware. So when we introduce new hardware into the data center, we do it on a cluster-by-cluster basis. And so we don't have any clusters that have some servers of this type, some servers of that type. One of the rules of efficiency and reliability in the cloud at scale is homogeneity. The more kind of mixed stuff you've got, the harder it is to diagnose failures and the more types of failures you're going to run into. Well, the implications of this are that if you deploy one of these A6 or A7 VMs, they will go through a cluster that has A6 or A7 capable hardware, which only some of the clusters do. And if you had a VNet that you deployed a cloud service into like that, and you want an A6 or A7, you're out of luck because the A6s or A7s aren't in the cluster that that VNet is in necessarily. So a tip is to anchor your VNets with your A6 or A7s. If you want an A6 or A7, which are the large VM sizes, create those first, put them in the VNet, and then deploy other cloud services to that same VNet, because the other way you might run into problems. Let's talk about the deployment steps. So the Fabric Controller processes the model, prepares the nodes by creating the VMs, putting the images down there for the roles that are going to go in those VMs, starts the virtual machines, and configures the networking. Their resource allocation. So how does the Fabric Controller decide where to put these, what servers to put them on? There's soft constraints, there's hard constraints. The soft constraints are, hey, let's put them close together. Hard constraints are, we got to honor fault domains and update domains. We can't put them on servers that, if they need to be in separate fault domains, they can't be in the same rack, because a rack is a unit of failure. And this is an example of fault domains, which you get with availability sets with IaaS, as well as when you put a role, your service gets spread across at least 2 fault domains, meaning 2 racks in the data center. Here's an example where if you see the front ends, 2 front ends, 3 back ends, they're spread across at least 2 racks. Here I've got them spread across 3. But now if we have a rack failure, top of rack router, for example, we only take out a slice of that app, not the whole thing. And this is where that 99.95% availability comes in the face of planned and unplanned outages. Here's how we guarantee that at least one VM of your application in each tier will survive that. And actually, we round robin. So basically, we guarantee half of the tier will survive a hardware problem that impacts server or top of rack router. So here's an example allocation. This web role, 3 web roles, large VM sizes. We got the worker role on the back end. We got 2 of those, and they're mediums. And the Fabric Controller will just find, these are cores on servers, so these are 8-core servers, which is what we used to have. Now we've got larger servers. But we'll put the front ends across at least 3 servers. Then the back ends will come, and oftentimes they get co-located just because of the way the allocation algorithm works on the same server as the front ends. Of course, these will be in fault domains, so those ones on the left might be in fault domain 0, then fault domain 1, then fault domain 0 or 1, that third guy. And then we wire up the VIP through the dips using SLB, like I showed you a little bit earlier. Let me show you an actual allocation using a tool that we've got called the Fabric Viewer. And I've got an application right here. It's a cloud service called Email Service. It's just a demo app off of MSDN. And I've scaled it out. You can see that I've got 2 front ends right here that are small VMs. I've got 3 middle tiers, worker roles, A, that are large VMs. And then I've got 4 backends, worker role B, that are extra large VMs. So these are 1 core. These are 4 cores. These are 8-core VMs. And you can see how with each one of these, they're spread across update domains as well as fault domains. So the backends are spread across 2 fault domains, 4 update domains. And the update domains are used for planned maintenance, like we update the host OS underneath them. We will only take out 1 of those VMs at any given point in time. Now let's take a look at how this thing is actually deployed. There's something over here called a deployment ID that you might have noticed in the portal. This deployment ID, where'd it go? Deployment ID. When you call customer support and you have a problem, they'll say, hey, what's your subscription ID? What's your deployment ID? And then they feed it into tools like this one, which show you a cluster. So we find out which cluster the VM is in. This is a cluster. You can see that it's 20 racks, like we've talked about. Here's the 20th rack. Each of these is a rack. Each of these is a server. These boxes represent VMs. And when I enter that deployment ID, what lights up in dark green is that application. If I click on this, you'll see, that is Azure Email Service. And it consists of 3 roles, like we just talked about. This is one of those extra larges that is worker role B, instance 3, which we saw in the portal. It's sitting on that server over here. Right there. There it is, that extra large. And if we go scanning through this to look at the yellows, you can see that they're spread all over the cluster, so they're all in different racks. Here's one of those front ends, the extra small right there, or the small. Here's a large, here's the small. Let's see, here's these medium ones. That's right there, one of the middle tiers. Those medium, or those large VMs that are 4 cores. And so the size of the VM, the size of the box indicates how many cores it is. These really tiny ones, those are extra small VMs. They're fractional cores. So that's one of the tools that we'll use to take a look at allocation. Now, when we deploy a role instance, we push those files, like I said, and the VM, the host creates the VHD, the host agent creates the VMs, backs them with those VHDs. There's a guest agent, if you're talking about PaaS, that talks to the host agent, and this is how we communicate information into your app, through that guest agent. And that guest agent is going to run your startup tasks, call your role entry point, it's going to start heartbeating you. The load balancer is only going to start forwarding requests into this PaaS VM once the guest agent says your role is up and ready. And what's happening is that the load balancer, the controller, is actually talking to the network, the SLB agent on those VMs and saying, is that VM reachable? When we talk about IaaS, the flow goes like this. You create a VM, RDFE sticks that VM or pulls the image out of the platform image repository. So if you watch the demos that I did this morning, you pick an image. If you're picking a platform image, it comes out of RDFE's image storage repository. It copies that image. It does a copy on write into your storage account. So this is an instantaneous copy like I showed you this morning. It generates an ISO. It passes to the fabric the fact that that storage account, that blob there with that VM, is the VM for the blob back in this VM. The fabric tells the host agent the characteristics of your VM and the fact that it's backed by this blob that's up in your storage account. Downloads the ISO, attaches it to the VM, creates a resource VHD, which is your temporary VHD, creates a cache VHD, which I'll talk more about later, starts the VM. And then there's an IaaS disk driver that is going to be faulting in data from that blob as your VM tries to access its sectors on its disk. This is the IaaS provisioning flow. Now this, so it's multiple steps. You can see it's kind of complex, but this is starting with the image. So this is you taking an image, and then what's happening is it's going to sysprep specialize that image, go through the multiple reboots, use the unattend.xml file to customize it just as you would do with standard Windows deployment. In fact, I'm going to show you inside one of these IaaS provisioning ISOs. Let's pull it up right here. I've got an ISO off of one of our test deployments. Oh, it's actually mounted here. This is using Windows mount from VHD, our mount ISO capability. And here's, actually, if you look back up here, there's unattend.xml sitting at the root of that ISO. And that's all pointing into this unattend WSF file, which you can see has 2 sections to it, just like any unattend would. One is the specialized pass, where we're configuring the paging file, the boot status policy, configuring certificates so it can talk to the provisioning agent, can talk to the host agent. setting the times zone, so pointing at our time server, setting the always mount disk SAN policy, because Windows doesn't mount SCSI volumes by default, unless you got this policy configured. Configures RDP keep alive. And then the second pass, after the system has been specialized, is where we set the administrator name, configure WinRM if you can determined it, set up BCD so that it can always boot from the same media properly, configure the licensing so that these things are automatically activated. We're pointing at our licensing server. And so you get the idea. There's basically, that's the end of it. Finally, when we're ready, we do ready. Here, we configure automatic updates. So this is actually all we do inside of this configuration of your VMs if you deploy the stock VMs from Windows Azure and you get them sysprepped by us. As far as the optimizations, we've done heavy work on optimizing the performance of the system. A Windows specialization can actually take up to 10 minutes. If you've ever done a sysprep generalize, you take the image, you put it on a system, first copy it onto the system, then boot it, and what it'll do is go through the specialization phase. After it's done with that, reboot into the general pass and get up and ready to go. We wanted to get our VMs up and running as quickly as possible, so we did two things to optimize provisioning of Windows Azure VMs. One of them is that we set the persist driver installation as part of our build process. So sysprep, there's an option you can pass to sysprep that says persist the drivers. What that means is normally sysprep will uninstall the drivers from the image that you're sysprepping. And then what happens is when you boot that VM, that image, then PNP goes, oh, here's a bunch of hardware. Oh, I need to go fetch the drivers. I need to go install them from cabinet packet files, or I need to go pull them off of Woo. And that will add to the provisioning time of your VMs. Now, we're always running on the same virtual hardware. So no reason to go through that discovery or go through that reinstallation of the drivers. So what we do is persist the drivers, and that saves 30, 40 seconds off the time of the boot process, is just having those drivers persisted. We also prefetch the blocks read during boot. So if you're familiar with the way Windows boots itself, it monitors its own execution and looks at the sectors it's accessing and creates a boot prefetch file. And the next time you boot the machine, it reads all those sectors in first and then boots. And so now what we've just turned is random I/O into sequential I/O, because the boot files are all slurped in because they're also defragmented. But they're all read in big I/O chunks into RAM, and then Windows doesn't have to go seeking all over the disk, waiting for I/Os to complete as the boot proceeds. It basically becomes compute-driven at that point. We do the same thing for our VMs, for our VHD images. Let me talk about how we do that. In the build lab, we boot these images that go into our gallery, and we monitor with a prefetch monitor the blocks. Oh, crap. I need to use that for a demo. All right, hopefully that reconnected. All right, so what's that going to do is create a prefetch map of the blocks or the sectors on the VHD that are being read while the VM boots. And sorry about that. I need to connect to CoordNet for this very next demo. So this was inopportune timing. Okay, hopefully that's going to work. So we get this prefetch map. What we do at the time of deployment is we download to the VM. We've got a prefetch driver, and we download the prefetch map to the server. And then we have our prefetch driver go pull those blocks in from the Windows Azure storage, the disk that you've created, the one in your blob in your storage account. We go pull those blocks down before the system boots into the prefetch file. And those are automatically populated in the host OS cache now for your VM. So when you boot up, it's not going to storage at that point. It's reading right from the local disk cache. Now let me show you just how dramatic that performance improvement is. So I'm actually VPN'd into Microsoft's CoordNet onto a jump server, and then I'm RDPing into a server sitting in an Azure data center where I'm going to show you VMs booting side by side, one with prefetch and one without prefetch. This takes a few seconds. Now let me explain what you're going to see. I'm not going to show you the whole boot, but when I fire up these VMs, I'm going to show you the size of the prefetched VHD, which is going to be about 3 gigabytes in size. What we do is we compress the prefetch blocks, we pull them back down and expand basically the cached VHD that's underneath this VM. So when we prefetched it, it has all this data that's going to be read during Windows boot process. And it comes out to about 3 gig of data during that sysprep specialize that's going to happen as Windows boots up. When we're going to look at the non-prefetched VHD, it's just going to be I think it's a few hundred megabytes in size. Very drastic difference. So what that non-prefetch VM is going to have to do, so here's the no prefetch VHD. So you can see it's 3 megabytes in size. It's just a stub VHD, basically the header and the footer, and that's it. Has no data in it. This is the cached VHD for the blob that's back in Windows Azure Storage. And then the prefetch VHD where we've pre-read, here it is, 1.7 gig of data that's been prefetched down to the server, done in huge IOs with multiple pipelined deep reads, so it actually comes down in just a few seconds. And now watch the difference in performance. Here's the prefetch, and here's the no prefetch VM. So I'll start the no prefetch VM first. Now I'll come over here and start the prefetch VM. Now this is actually a Windows Azure server that we're looking at with VM Connect sitting on the server looking at these VMs. And now, oops, I'm not sure why I'm seeing that. Now what we're going to see, assuming that the demo was reset appropriately, is, yep, so you saw that flash. That was one part of the sysprep phase right there that we've already passed through. We haven't seen the flash on the right side. This thing is actually minutes slower than this side. So getting devices ready, wait to see how long it takes to get devices ready on the non-prefetched version as it's pulling in data from Windows Azure Storage, the blob that's backing that disk. The VM on the left is going to reboot in a second after it finishes specialization. Here it goes. The second VM, we haven't even seen that getting devices ready yet. The non-prefetch one. And in another few seconds, this thing is going to be ready to go. We just saw another flash from the right side. That's how far behind it is. And another few seconds here, and we're going to be at the login screen for the prefetch VM. This guy still hasn't rebooted on the right side. The total time, I know it seems like a long time as we sit and watch it, but it comes out to about 1.5 minutes for that prefetched VM to boot up. This guy's still on getting devices ready. And here we go. You see the screen's blanking. We're going to end up in the login screen here in a second. There we go. So this guy still hasn't booted yet. That's the kind of performance optimization that we're talking about that the prefetch does for us on the platform. Speaking of performance, our goal for booting Windows VMs is less than 6 minutes, to have all VMs boot in less than 6 minutes. We're actually way hitting that. This chart is actually what you perceive from the portal, from the VM being ready. And you can see that the 6-minute mark here, this is based on VM operating system type. And so here's Windows Server 2012. So then at 5 minutes, we're about 85th percentile. At 6 minutes, we're at the 90th percentile. And you can see that we're actually continuously bringing this down. And in fact, one of the things I mentioned in my earlier talk is that there's actually delays built in to the reporting of the status of the VM. It's actually booted faster than we report it to you by about 1.5 to 2 minutes. So we're actually well below 6 minutes. It's just we need to get rid of those reporting delays. But you can actually RDP into the machine in about 3.5 minutes. And Linux is a little bit faster, I'm embarrassed to say. But I'll be brutally honest, I'm not hiding anything from you. That if you really want fast VMs that can't do as much as Windows can, then you can go with Linux. Just kidding. Now, the tail of deployment times, if you ever run into one that takes a really long time, it's almost certainly that you've landed, unfortunately, on bad hardware, which happens occasionally. There's bad hardware in our, when you run at scale, you're going to have that. Let me take a quick look at deployment performance and the breakdown of things that happen. You can see, using this deployment viewer, this IaaS deployment. And if we go to Fabric Update Tenant, you can see here are the different phases. Here's the creating of the VM right here. And you can see from this, the creating of the VM took about between second 29 and second 49, so it took about 20 seconds. Then we start the VM. That took 7 seconds. Then we set the container role state. We boot the VM. That took about 30 seconds. And then here's where the provisioning agent actually comes up and starts doing the sysprep specialize, generalize, which is the remaining amount of time. And you can see at 3 minutes, 38 seconds, the VM is ready. You can RDP into it. Then there's delays as we go up the stack. This is where RDFE right here sees the VM as being ready, which is, in this case, it was about 4 minutes. And then the portal has extra delay on top of that. So that's a look inside of the actual deployment as captured through our telemetry that we have on all our VMs. So if you've got a VM problem, this is the kind of stuff that we can go look at to see what happened. I'm going to skip actually updating services and go right to our disk performance, because I think that you might find that a little bit more interesting. And talk about our disk architecture. Underneath our VMs, we've got, in our case of our PaaS VMs, we've got 3 disks that are visible to you. One is the OS disk, one is the resource or temporary disk, and then the third is your role VHD. And these are all VHDs. You can see some of them are dynamic VHDs, some of them are differencing VHDs. The host OS is a differencing VHD. They're all sitting on local storage on the server, attached to the server. These are SCSI disks on the server. We've got 6 of them. Sorry, 6 disks. 5 of them are what the VMs are running on top of. They're striped. It's a Windows stripe. If you take a look at our IaaS VMs, they look a little bit different. We've got a resource disk as well on those. We also have the host OS cache that we were just looking at, that VHD. Those are all in the stripe as well. Now, the data disks, which if you don't turn on caching on those data disks, they are not backed with anything on the local storage of the server. They're backed completely by Windows Azure Storage. Now, the default cache policy is for the host OS to be cached for performance. This is what gives good boot time, is not having to go to Windows Azure Storage for very small IOs and lots of writes that Windows does. But you get the best performance for your databases if you go to Windows Azure Storage. Much more IOPS can come out of Windows Azure Storage than off of those local spinning disks. Let's take a quick, well, here's a chart. You don't have to memorize it. You'll get the slides. But this will show you, see, a temporary disk, which is the same architecture for both IaaS and PaaS. This is where the paging file is placed. You can see that that's a maximum size of 2 terabytes. It's a dynamic VHD. Your performance is going to vary on that based on if there's other VMs active on that stripe. So it's not something to base your performance testing on and your mission critical stuff on. The same thing goes for the PaaS OS disk, the PaaS role disks. Those are all on the stripe as well. You can see that the only things that are not on the stripe are the persistent disks for the IaaS, which are backed by Windows Azure Storage. The cached ones do have caches that are on that local stripe. So, and the thing about this server disks, all the VHDs on that server, they could be lost if the server fails. So don't put anything that you care about in those VHDs, on those disks, on those VMs, if you care about them, because if your VM ever moves from one server to another, you're going to lose that data. Let's take a quick look at disk performance. And I've got 2 examples to show you here. I'm back in this VM right here that I was showing you, and I've got a tool called Iometer. And Iometer I've got hitting with small IOs. So this is 8K IOs hitting a data disk that's not cached. So it's a non-cached data disk backed purely by Windows Azure Storage. It's a 100% write workload. Even if it wasn't, all of the IOs would go to Windows Azure Storage because there's no local cache. And you can see that it's coming to close to 1,000 IOPS. And this is about what you get off of one disk today in Windows Azure from your IaaS VMs backed by Windows Azure Storage. This, we're going to actually end up capping this. So today we basically run on throttle, but in the next couple months we're going to be throttling IaaS disks to 500 IOPS. So we're actually seeing more than 500 IOPS here. When we put in the throttle, you'll see a maximum of 500 IOPS. If you want more IOPS, create more data disks. And if your application can stripe, or you can take advantage of Windows Azure striping, you'll now get the combined IOPS. So put 16 data disks, and you're going to get, what, 16 times 500, which is, what, 8,000. You'll get 8,000 IOPS off of your extra large VM for small IOs. The host OS disk, different story, because you're now talking about, so if I go to C drive here and run that same test, we go take a look at the IOPS, what we'll see is the local spindles shining through. And this is 100% write work through, right through to those local spindles on the stripe. So we're going to see somewhere around 50 to 100 IOPS. And that is the native performance off of writes to the storage stripe. We'll see much better performance if we do reads off of the host OS disk because there's a read cache there, like I mentioned, for performance. Now that cache is of limited size. And with this iometer test, I've got a 30 gig file behind this test, which is too big for that cache. But I've got a SQL I/O. Let me bring up SQL I/O. I've got a SQL I/O test, a random 8K read off of a 10 gig file off of that C drive. So the C drive, remember, is the host. And when I run that, this will take 60 seconds. And you're going to see some amazing IOPS coming off of the read cache because everything basically is not, it's also backed by RAM. And so the read performance we're going to get, because everything is sitting there right on that server, is just going to be phenomenal, like it blows your mind phenomenal kind of performance. How phenomenal? Let's take a look. A minute takes a really long time in front of an audience, doesn't it? When I say striped, what do I mean? I mean Windows software striping. That's not hardware stripe. Without parity, correct. So that's good. Let me come back to that because we're just about out of time. Here's the slide with the tip on disk performance. Each IaaS disk type has different performance characteristics and different purpose. The OS disk has a local read and write cache optimized for small working set IOs, tuned for booting the OS. Don't put anything except for small databases on that. Put your heavy-duty databases on a data disk, and if you want better performance, put them on a striped set of data disks. Now, don't use Windows striping underneath SQL. SQL knows how to stripe across disks. So use SQL striping for best performance. SQL's own support for spanning a database across disks. But if it's an application that doesn't know how to, it's not stripe aware, then you can create a Windows stripe and get those IOPS like I talked about. Temporary disk just for local cache storage and for the paging file. And unless it's small, like I said, put it on a data disk. The other thing is, for anything that is backed by local storage, any of these caches, you're going to get the best performance out of your VMs if you fully populate the caches before you start hitting your workload. And the way you do that is by touching your workload, basically, your hot part of your working set, faulting it into the cache. What that's going to do is bring it onto the server. It's going to expand those VHDs, so you're not paying VHD expansion charges as your workload runs. So just a tip, prep. Other tip, hit Windows Azure Storage hard, and it starts to listen to you. So what it'll do is it sees hot blobs, and when there's two hot blobs on the same server, it'll move them. It'll not move the data, it'll move the compute processing for those blobs onto different servers. This is something called splitting in Windows Azure Storage. And the hotter you hit it, the more times you'll get split off until you're basically on your own servers for your storage performance. So when I was showing you that test run there of getting close to 1,000 IOPS, that's after I'd been hammering that blob for about 40 minutes. My performance went up from 400 or so IOPS up to 900-ish, 900, 1,000-ish, as storage started to split me from other hot blobs that were competing with me. Let's go take a look at that. So how many IOPS did we get off of that? We got this number of IOPS off the read, SQLIO read, and that's 85,000. So I told you it would blow your mind. It's a lot of IOPS. And that's what you get off that local cache. All right, so I'm out of time, so I'm going to wrap it up here. What I covered was everything from the network hardware topology that has evolved in Azure to the way that we've got the software architecture on top of that hardware topology, how applications get deployed, how we create those VMs, look underneath the hood of how we deploy the IaaS VMs and do sysprep specialize, the performance goals that we've got, and finally talking about how we do storage architecture underneath these VMs from local storage for PaaS, cache storage for IaaS, as well as IaaS XStore, Windows Azure storage behind these blobs and the different performance characteristics. What I hope you get out of this is okay, how do we run things at scale at Microsoft? We're building this massive hundreds of thousands of servers kind of infrastructure because a lot of learning has gone into what you see presented here. Also, I hope that you got, whether you're looking at the platform or playing with it already, some tips to help you optimize your applications and your workload usage based on actually this internals information. Because each one of these tips you can see maps directly to something I showed you about the way the platform behaves underneath. So with that, I hope you enjoyed it, whether you're going to use Azure or not. And I hope if you aren't using Azure that this encourages you to take a bet on our platform, that we really do. This is serious engineering that we're doing to make sure that we deliver great performance and availability, reliability for your applications. Please fill out an evaluation, and thank you very much for coming. I've got 2 more sessions, both on Friday. One's on malware, one's on Windows troubleshooting. I hope to see you there. I hope you have a great week at TechEd, and see you Friday. Thanks a lot.